Motor controller testing. I've been debugging the board for like 3 days till now, and there were some bugs found. But like the major issue is like the motor will jitter when running, and like I couldn't find the like what caused that. There were several other like minor bugs found during the process, and I fixed those, and I've like shoot a video on each of those. But like now, okay, so firstly I forgot to upload, and now like I don't think that's worth a separate video, so I'm just going to compile them into this single video. So yeah, so firstly, to start off, we're using a I2C encoder, right? Which is running at fast mode. Okay, that was something I also didn't got the chance to change. Actually, this one I found the solution while I'm sleeping, so in a dream. That's pretty amazing. So yeah. Anyway, the issue is like when setting the I2C mode to fast mode plus, the encoder will stop working when there's current spikes on the like the supply like VCC voltage. So that may be due to a signal integrity issue. The encoder is rated to run at like fast mode plus, so 1 megahertz. But I just couldn't get it working. So like during that dream, I thought of two possible issue. Like first one, the pull-up resistor on the encoder board. This is the board from Amazon, and I forgot like what value they use for the pull-up resistor, but like for high speed fast mode plus, I think it requires pretty low resistance, like 1K or even like 270 ohms, 417 ohms, and so pretty low. The normal like 10K pull-up won't work here. So yeah, that is a thing to fix. And also we need to change the GPIO setting here to make it like the speed of the bus, to make it fast speed instead of the low speed, like by default. Yeah. That's the signal integrity issue. And also I discovered a bug or feature in the ST's I2C library. So in the encoder part, oh my god, this focus. Okay, we can see it clear. In the encoder like library, I was using this function each time I'm trying to pull the data from the encoder. And like how I2C works is like you need to, when you are reading data from the slave device, you need to first send a I2C write frame to write to the, like basically to tell the slave device which configure register you want to read from. And then you send the I2C read frame to like read data, so that slave will transmit the data back. So that's 2 frames. And like ST, they included this function, so you can just combine those 2 requests into one single function call to read from a memory address. But like it is an interrupt, right? It is supposed to be non-blocking, but actually I noticed that like this function will stuck for like about it will account for like half of the 4 kilohertz cycle, so that's 1 kilohertz 1 microseconds. Yeah, anyway, it's a long time inside the program spent inside this function. So like then I started to look into it and see like what's going wrong with it, and I noticed like they are using timeout things, which turns out that like in this function, it will first transmit the write frame and then transmit the read frame, and then goes into the interrupt. So that is a pretty significant overhead in this function, which in turn limits how fast we can pull the position sensor. So to change that, like fortunately the AS5600 encoder, it supports like storing that configuration register address inside its own like memory, so that like during the initial setup we can issue a memory read command, and then we just need to continue sending the pull command, like the that's confusing terminologies. Like firstly we need to transmit the entire like write and read sequence, but afterwards we can just issue the read commands, and it will like automatically transmit whatever address we previously requested and return the up-to-date data. So that's a thing to change. So like during encoder setup, we do the setup to tell it which address we want to read from, and then in the actual interrupt routine, we can just like send out the read request, which like this one is purely non-blocking. It's very small amount of overhead. Yeah, and then we receive the data in the I2C, like separate I2C complete routine. I think it's somewhere. It's here, yeah. And because we changed the function, so we're using a different interrupt handler now. Okay, that's that is the I2C part. But after changing that, I still couldn't get the motor jitter to go away, and like the symptom is like I've tried to log the current sampled in the like the phase current, and it turns out that there are some spikes when running. So like there's all the perfect like sine wave, and then there's a spike, and then spike, and the jitter frequency is actually about like 3 Hertz. So like the motor in the position control loop, it will respond normally, like it will try to go back to its original place, but then like every like on a 3 Hertz cycle, it will like go like there's a sudden torque, like that, like those. So I've tried to use the open loop, so I directly command the IQ and ID to the motor controller and let it spin. It spins perfectly fine, which means that the math is correct. At least the inverse Clark and inverse Park and like SV PWM math is correct. And then I tried to like check like whether the Park and Clark transforms are correct, but like originally I was printing out the IQ and ID current, so I was suspecting like there can be some math issues resulting in a incorrect value, but later on I printed out the 3-phase current, and they were jittery. So it turns out that the solution or the cause of the problem is I was using so there are 2 ADCs on this like STM32G4 device, ADC 1 and 2, and like I'm sampling 3-phase current, so there are 3 I'm using 3 onboard op amps to connect to like those ADCs to read the result, and like ADC 1 is in charge of reading phase A current. It is phase A, right? Yeah, I think yeah, it is phase A, and ADC2 is in charge of reading phase B and phase C. So I've tried a bunch of different combinations, including how the timer is triggering the ADC and all those various settings. And I got different error results, but like the most up to date from this morning is like current A will be freaking out, and current B and C are running perfectly fine. So I tried to look into like what different ADC configuration I'm using between these two, and it turns out that ADC2 is not using the regular conversion. It is only using the injected conversion mode to sample the two op-amp readings, while the ADC1 I was using both the regular conversion and the injected conversion. So injected conversion, there was one channel for the phase A current, and also like we need to read the bus voltage and temperature and the onboard potentiometer, and we don't need that to be high frequency sampling. So I'm using regular conversion mode, which is triggered by a lower frequency timer 4, also running at the same frequency as the position loop, 4 kilohertz, I think, or 2 kilohertz. And that was the issue. So I'm still unclear about how exactly there's a problem, but like I think from my understanding, so ADC it will do conversion, sample and then conversion, right? And like injected, when there's an injected trigger coming in, the ADC will abandon the current ongoing regular conversion and reset the ADC, sample the injected channel, and then do the conversion, and then goes back to the regular conversion. And I think the problem is like it takes time, and during the reset phase, I don't know why, but like it seems that the injected converted data will also be reset to 0. So when I'm sampling the FOC phase current while the ADC is during the reset phase, I will get a 0 reading on the phase A current, and that is a big spike because like I need to offset the data and then multiply by the coefficient, so it will result in a huge current. And the FOC program will capture that and try to fix that, so it will tune the motor phase current to like the set point to very large value. Yeah. Oh, and also an interesting point, like it comes to me now that because I was using a filter, an IIR filter for the phase current, or not the phase current, the converted like IQ and ID current, because they are rippling. Because like phase current sampling, it isn't precise at all, right? There's a huge amount of noise during each conversion. So like we need to filter it in order to get a kind of like a steady, stable reading. So in the power stage, when reading the current, or not in the power stage, the current controller, there's a oh yeah, it's this one, the current like IQ and ID filter alpha value, which is used in the motor controller code somewhere down here. Yeah, it is this one. So like now I haven't fixed the code. So the symptom was like I was able to configure the alpha to 1, and the motor runs kind of fine, not perfectly fine, but pretty fine. But any value other than 1, like 0.9, 0.8, like we're supposed to run at 0.1, I think. Some code even use 0.05. So like then it didn't work well. It will jitter out. So I think the result of that is, because I'm getting those 0 readings from time to time, and if there's only like 1 reading erroring out, there's no, it will not interrupt the other loops. So like there will just be a spike in the output, but like it's only 1 PWM cycle, so that's very small. The motor don't have enough time to respond to that, and it's fine. But like with the filter, like the spikes will like last for some time, so it will cause the issue. And yeah, that's probably why. And I was doubting, like, it's just a filter equation, and then like any other value, it won't work. So I was very confused about this. Like the math couldn't be wrong. It's so simple. Yeah, so that explains this. And yeah, so the solution to the problem is just like, I'm not using the regular conversion channel now. So to like we still need to sample the bus voltage and also temperature, the input pot, and I'm using the injected channel for all those. So yeah, the data will be sampled every PWM cycle, but there's not much disadvantage to that. And the sampling time, I think we can try to maximize it so that it spans the entire PWM cycle. So it must be shorter than when the next PWM cycle comes in, and like we need to sample a new current, phase current. But that is some time, and I think it will be enough. And also we can do some software filtering, just like the IQID thing, to make it more stable. So yeah, this is the temporary solution. I think there will be other ways out, but like I'm sticking with this. And also I've tried to study the official code provided by ST on their like generated by their motor control SDK, and they were using, I think this is pretty smart. So we need to trigger ADC on the correct time to sample the current, right? Because like we need to sample the current when all the three phases are like the low side are open and the high side are closed. Can we sample the current? So in the timer 1 setting, and also I've tried to study like what's the how timer work in exact. So this is the timing diagram of the timer. So this is the counter. It will go up and down in center line mode. And mode 1, mode 2, mode 3, it doesn't matter when we are all using PWM mode, because it only matters when there's output compare settings and we're using none. So yeah. So center align mode, the counter will go up and down. And there's these three are phase output. And this is like the threshold register of the 3 phase. And by default, so in PWM1 mode, the phase output will be high when the counter is lower than a threshold. So like when during the 0 point, if there is any value, the 3 phase will always be high. And during the ARR, like the top level, the 3 phase will be low. So we need to sample when the counter is at the ARR value, not the 0 value. And that is inconvenient because then we need to set the trigger for the ADC to be ARR -1. to be able to generate a pulse like here, instead of setting it to 0 and generate a pulse here. Yeah. And the alternative way is to make these 3 guys be PWM mode 2, basically inverting the phase. But then, like, when we are writing PWM output, 0 means the maximum output and ARR value means the minimum output. So that's all inverted, which is inconvenient. So I think this works fine. We can also try to configure the polarity of these channels. But it's pretty complicated. And I'm not sure whether I want to do that. Like, this works fine as long as I can remember to change it. Yeah. And also, afterwards, like when the motor is working now, and I've also upgraded the control loop to make it run at 20 kilohertz instead of 16 kilohertz. So a bit faster now. And we can see, like, open the switch, and now it runs at like idle mode. There's a built-in brake on the motor, and we can switch to position mode, and it runs very smoothly. There's some audible noise here. I'm not sure why, but I think it's fine. That's fine. 20 kilohertz. We can go even more, but we need to first optimize the code to make the FOC loop run faster. And yeah, see you.